Hello, everyone. Welcome to this presentation about how we can use Wireshark to analyze and possibly troubleshoot IPsec VPN. I'm Jean-Paul. I've been working as a network and system engineer for almost 40 years now. And since 2010, I'm running my own company as a consultant and a trainer. And I'm also an author, so a French publisher named Init. As you probably guessed, I'm French, and so please forgive my accent and also the potential mistakes I'm likely to make during this presentation. On this presentation, I will talk about IPsec VPN, but I choose to focus my presentation on site-to-site IPsec VPN and also on the version 2 of IPsec, since you probably know that there are two versions, 1 and 2. The version 2 is now has been promoted as a standard, I think, in something like 2014, I think. Now it's most commonly used, but we still find version 1 IPsec VPN. If I have some time remaining at the end of presentation, perhaps we could have an eye on some catch-up with version 1. I will deal mainly with two cases. The version 2 without any network translation between the two sites, and also a situation where there is some translation occurring between the two sites. We will also have an eye on some cases where troubleshooting is possible with Wireshark. And for all these cases, I will use both unencrypted and encrypted packets to compare what we can find in the packets when they are encrypted, and if we can decipher them, what we can find into them after deciphering. And so we will also see the situation where the deciphering or decrypting is possible and what we need to decrypt these packets. Let's see what topology we will use for most of the cases we'll see during this presentation. We will use mainly two sites, site A and site B, linked with a pseudo internet network and without any translation between them. And also there will be also a third site, site C, which is behind the site B. So there will be some translation occurring between the site C and site A, for example. For this presentation, I will use some captures files and also some profiles. You can find them in the Zoom channel number 1. I think it's a file name example captures, a zipped file. And in this zip file, you will find something like that. And we will use the first example we will use, to be more precise, is the IK v2 no nat .pcap file. If we open this file, we will find this kind of packets, for the moment without any deciphering. And to summarize the situation. Monad between the endpoints router, we will use the following public addresses, and behind the devices, we find two subnets. One is a 10 subnet, and the other one is a 203.net. Okay, so we will use this file to see how IK version 2 works. First, in fact, IPsec VPN are a bit complicated, and to be honest, I'm in no way an expert in cryptography or IPsec topic, but I'm just trying to make the knowledge accessible to the largest population. So I would keep to something rather simple, in fact. So the creation of the version 2 VPN includes two steps. The first step will see the creation of something named IK Security Association, that is not named also Parent Security Association. This is the foundation for all the exchanges that will lead to the real user data exchange. This is the first step. In the previous version 1, the name was very often, this step was very often named phase 1. And the phase 2 of the version 1 is now more or less included in the creation of the IPsec Security Association. They are named also Child SA. And so we need one parent SA, and from this parent SA, we will build, or on this parent SA, we will build one or several child SA with one SA in each direction for the tunnels. What is also very important to know is that there are two roles dedicated to the site. One is initiator, the other one is a responder, and these roles could be different in the different steps of the VPN. One site can be initiator at the beginning of for example, the parent SA creation, and a bit after, being the responder for some other exchanges. Also, something that is rather common is that the message are in pairs. There is one request and normally one response. For the establishment of the first step, we can examine the packets in this capture file, and we see that there are 4 messages. These 4 messages, we can see that at least the first 2 are based on the port 500. They are based on UDP protocol, and the protocol included, or the name of the protocol, is Iksa KMP. In this exchange, this first exchange, we can see what is included in the exchanges. So it means that these first packets are unencrypted. They are named usually IK Init. What can we find in these packets, in this message? let's start by the first one. The first one, we have something very important. It is the SPI. SPI for Security Parameter Index is a value that is used for identifying the traffic and directing the traffic to the correct security association. For the moment, we can see that it's site A that is initiating the connection. So there is a value for the initiator SPI, but a value of 0 for the responder since it is the first exchange. We can also see that we are working with the version 2. It's indicated there. And after that, we have different flags. We have a flag for to define what is our role, initiator or responder. And this message, is it a request or is it a response? We have also a message ID. This message ID is useful since it permits to follow the answer related with our request. For example, there we see that there is, that's better. We'll see that for the two message Iksa init, we have only one value, 0, for the message ID. So we have the answer to the first message there. This message ID could also be used to put in place an anti-replay mechanism to fight some attacks, to detect when some packets are replayed. So after that, what is useful there? The number of proposals, for the moment only one. In this proposal, we have some definition of algorithm that site A proposed to use, author to use. We have also some data for the key exchange, some nonces. And after that, something that could be interesting sometimes, it's the NAT detection fields. For the moment, we know that between site A and site B, there is no translation. But if there was one, it could be a problem because IPsec VPN and network translation doesn't work very well along. So to detect this potential translation, there is two fields, one with a combination of addresses of source and port, and also some other data, and the same thing for the destination. And this is sent to the other side, and they will compare, and they will compute the same thing on the other side. They will compare the two values with their own values, and if something is different, that means that there is a translation along the path. And so, if there is a translation, we will see in a couple of slides that there is another mechanism that will happen to help us to carry the VPN, although the NAT translation. There is also some algorithm for the signature, and that's all. Same thing for the as for the answer from the other side. And we have also some details with the compression detection and the some options supported, this kind of thing. And that's all. After that, we'll find two other packets, but in these packets, we see less useful information. We can see the flags, an ID for the message, and after that, the data will be encrypted. So we are becoming a bit blind to go further. In these exchanges, I can tell you that these exchanges are mainly related with identity, with secrets, and also these messages 4, 3, and 4 also concur through the creation of the first child. After that, for the other child essay, there will be other messages, but for the moment, for the first one, the creation is also beginning in these two messages. To see what we could have in these messages, we need to decipher them, and what we can have after deciphering. So there I have the version without any deciphering. If we change of profile, if you have got the profile with the zip file, you can switch to the VPN complete profile, and then in this case, I will have some further details. For example, for the packets 3 and 4, now I'm able to see more details. And in these details, in these fields, so there are some changes. There is the encrypted data as previously, but now there is a subtree decrypted data. And in this subtree, I can see that there are some identification, for example. In this case, to identify the sites, we can use the fully qualified domain name, the vpn10.examples.pro, for example, for this site, and vpn30.examples.pro for the other site. And this is a critical point, since it's a cause of failure when the identity are not correctly set up in a VPN. So with this information, we can check what identity or identification data the sites are using or are proposing. After that, there are some algorithms, and also after that, another point of failure, or rather current, is the traffic selector. Traffic selector is very important in IPsec because it's the criteria to route the traffic to the VPN or outside the VPN. And if we don't define correctly the traffic selectors, we can have some traffic that are expected in the tunnel, but it goes outside the tunnel, or some traffic is directed into the tunnel, even if it is not pertinent for the other site. So it's important to be able to see what traffic selector is defined. We have the traffic selector, where is it? There, for one side. So we find the subnet behind the firewall for one site. and the other one. And it's compulsory, or at least in version 2, it could be different, but it's better to have a symmetrical definition between site A and site B. And that's all for the most important information. After that, we have the child essay that is created. So we can, after that, exchange user data. And this user data is or are exchanged with a specific protocol named ESP. If I go back to the undeciphered version, this is what we can see with Wireshark. Not a great amount of things. With this packets, we can see that we are not in UDP or in TCP. We are in a specific protocol. This specific protocol is identified by the number 50. And so it is rather autonomous towards the usual protocols, TCP and UDP. And in this case, the only thing that we can see in these packets are one SPI that is different from the IKE SPI we have seen previously, and one sequence number. These two elements are visible in encrypted packets, and they are still useful, since the sequence number is also useful to follow the packets, to see if there are some gaps in the numbering of the packets, or also to fight a potential replay attack, because they are supposed to always increase one by one these sequence numbers. And when they reach the limits, since there is a limit, we are forced to renegotiate another SA. There is one SPI in by direction. So there is, we can see that there are two sequence number 1, two sequence number 2, etc. But they belong to two different SPIs. So there is no replay attack. There is no there is abnormal traffic in this case. If we want to see more, we can, but in this case, it means that we have to decipher the ESP exchanges. Yep. And if you switch again to the VPN complete, in this case, we can see the actual traffic in these ESP packets. We see that in this case, it was a ping exchange that was carried by the VPN. So we are able to do the same thing that we can do on normal ICMP traffic or IP traffic, whatever it is. We still have the indication that it is an ESP packet, since we see the sequence numbers in the columns. In the details fields, we see some additional fields linked with the some authentication and integrity data, and that's all. So That is interesting to have this deciphered packets, but is it possible to have it rather easily? The short answer is no. Because what do we need to decrypt the traffic? First, to decrypt the IKE version 2 packets, we need first the SPI numbers or values. It's very easy to do to get, since we have this information. Yep. Switch back to the no decrypt profile. We have this information included in the first exchanges. That's the easy part. The less easy part is to get the encryption keys that are used by this first step. And it's not very common to have these keys available. For these examples, I've used on one site a Strong-Swan package on our Linux system, and the other system was a commercial firewall. And on this device, I'm not able at all to have some encryption keys directly accessible. But on the Strong-Swan, I'm able to have these keys if I upgrade the log level to the level 4. Perhaps the commands or the methods could be different from one distribution or one package or one version to another, but the command I've used in this case is IPsec stroke level IK4. And in this case, and if I'm beginning since the very first exchanges to the log at the level 4, I'm able to see these keys. So it's only at the creation of the IKSA that these keys are recorded in the log. I will show you how it appears on the logs. There are actually 4 keys that will be useful and necessary for the IPsec deciphering process. 2 keys for the encryption, 2 keys for the authentication, 1 for the initiator, 1 for the responder. So in the log, they are not. I cannot find the consecutive strings, but I have to copy all these bytes and put them somewhere in Wireshark. And somewhere, if I start by the no decrypt version, somewhere is in the preferences screen in protocols, and in protocols I will look for Iksa KMP protocol, and on this screen I've got 2 buttons. One is for the version 1, and for our current version it's button ID2. For the moment it's totally empty, but if I look at my profile, at my other profile, my complete profile, I've already entered the necessary information. So if I go back to protocols, KMP table for version 2, now I can see that I have the SPI for each one. I have the encryption key, the encryption algorithm that is necessary to. It is necessary to precise what algorithm we will use, and same thing for the authentication keys and the authentication algorithm. And if everything is okay, I can hope to have a result that is rather satisfactory. And I have to repeat this process each time that the IKSA are recreated. And as normally the step one, the parent essay, is regularly negotiated for to avoid possible vulnerability and exploitation. You have to regularly look for new version of the keys in the log files. So it's a rather tedious process if you have to examine a rather large file. Now, if we look at the ESP packets that are the more interesting packets since they are carrying the user data, we need also the SPI, the ESP SPIs. That's the easy part. The algorithm is easy also. And as for the IKSA, the most difficult part of the task is to get the encryption and authentication keys. And on strong one, you are able to get them with also at the log level of 4 with a specific command that you can give whenever you want. And this command displays the necessary keys. You have just to copy and paste these keys in the preferences screen of Wireshark. And to be more precise, I have to go to preferences, protocols. In protocols, I look for the ESP protocol, and the button ESPSA brings me to this screen where I can enter the addresses, the ISP, the encryption algorithm, the encryption key, and same thing for the authentication algorithm and key. And if I'm lucky, I will get something rather interesting to read. That's the first part of my presentation, the presentation without any translation. If we want to compare with what happens on a translation case, we can use two other files, the example NAT-C and NAT-A. So in this case, if you remember the topology, the VPN will be created between these sites and this one, but the device B will trigger some translation. So let's open these files. First one, and second, just in case. So, up, and for the moment, I will stay without any deciphering, any unciphering. So we still have our 4 messages. Don't pay attention to the first 2 messages. I think that was a remaining capture, but the exchanges start at packet 4 in this case. So we find again our SA init packet. Is there something very different? For the moment, it's not obvious. We are working on the 500 port, so everything as usual, I would say. But after that, it's not, it's often the case. We, for the packet 3 and 4 of the exchange, we are switching to the 4500 port. But the main difference is after that. If you look at the ESP packet, we can see that now it's not a very specific protocol, the 50 protocol, but it is based on a UDP protocol on the port 4500, but it's based on UDP. And why it is useful? It's because to overcome the problem of the translation, because the ESP native protocol is not be implemented with the translation in mind. It's impossible, or almost impossible, to carry this protocol with a tunnel protocol and some translation. So the switching to a protocol like UDP or TCP brings the ability to use ports, and in this case, we can provide the user data with the packets with the user data with the help of the UDP ports. And the commonly used port is the 4500 port. After that, business as usual, I would say, regarding the content. We can also see all of the exchanges. In this case, it's a very short exchange, but in this case, we also see other exchanges. For example, a NAT keep alive exchange. It's not typical of the translation exchanges, but we can also have some informal exchanges. We see also a create child, a specific create child exchange. I've told you before that the first create child was included in the 4 messages. There it is a specific exchange to create another child, to recreate another child. We'll see after that. So just to talk about the NAT keep alive packets. This NAT keep alive packet, as its name could indicate, is there to maintain the translation table on the device that is translating the packets. Because if there are no user data on the tunnel, into the tunnel, if there is not a mechanism to keep this tunnel open, the risk is that the firewall B close the NAT entry in the NAT table, and the tunnel won't be able to work anymore. So this NAT keep alive mechanism forces some exchanges, even if there are no user data, to maintain this NAT entry in the table. We don't have take care because we don't have to assume from this keep alive that the peer is still alive. In IPsec VPN, we have another mechanism that is compulsory in version 2. It was optional in version 1, that is named dead peer detection. This is the very one mechanism to help us to detect if the peer is dead or not. For this function, we cannot use the NAT keep alive. NAT keep alive is only is only intended to keep the NAT entry. Normally, the receiver side doesn't have to manipulate this data. It's only for the intermediary firewall. And what? So if we sum up the differences between NAT and no NAT, the port for the ESP, the NAT keep alive, and also bizarre thing is pardon, the right one. Where is my? Yeah, there I am. There is a very specific field because we have two different traffic on this port, on this UDP port. We have to distinguish. We have something to help us to distinguish what is what traffic is an IKE traffic and what traffic is ESP traffic with user data. And for this, when we use the port 4500 for IKE traffic, we have a very specific marker named non-ESP marker. And to be more precise, if we have the packet bytes somewhere, this non-ESP marker is it's a field with 4 zeros value. And instead of this, in ESP packet, we have at the same place, we have the SPI. So, and as the SPI, at least for the ESP, cannot be 0, each zero value packet must be an IKE packet. Okay. Let's switch to some cases rather quickly. First one, we can use the this file, troubleshoot site A and site C. In this case, the VPN are established. One side is SONG1 server, and the other site is a commercial device, but we see that we have an active tunnel. Nevertheless, no traffic is able to go from one laptop to a server, for example, between the two subnets. So what could be wrong in this case? If we open the troubleshoot, so it's this one, I think. Just check. Yeah. So I'm on site A at the and in this case, the beginning of the file is not relevant. The real beginning is after that. Packets, let's say packet 20. So in this case, we are on version 1 VPN, but it's not a problem. It's problem will be the same with version 2. The main point is that we see that we have exchanges for the IKE parts, so it's okay. And after that, we see the ESP part. So when we see ESP part, it means that the first step has been completed, since we cannot have a child essay without a parent essay, or a phase 2 exchange without a phase 1 exchange valid. So in this case, that means that we are at the step where the user data exchanges could happen. But and we see that all firewall send some data, but if we look at what happens on the other side, so site C, we see something rather similar. We have ESP exchange, but what is rather bizarre in this case is that we see only exchange on IKE level, on the port dedicated for IKE exchanges, but no thing apparently come back from the other side. So we know that we are able to send via the tunnel, but apparently we are not able to receive. In this case, as you see there, to infer this this from what we see, we don't need any deciphering process. With only these packets, we can point that there is a problem between the two sites, and some traffic are deleted between site A and site C. So we can probably infer that there is something filtering the traffic, and in this case, it was another firewall that was permitting the IKE exchanges, since the IKE exchanges were occurring on the UDP, and UDP was allowed, but specific protocols like the 50 protocol, and ESP is a very specific protocol, was forbidden. So it was a reason why we were seeing something apparently normal on the firewall, on the VPN point of view of the firewall, but not running smoothly on a packet capture point. Another one, in this case, nothing established. No IK, no child, no IPsec SR. In this case, we could open the troubleshoot IK packets, perhaps there. This is a very, very short file. What can we see in this particular file? We see that something is initiated by the site. In fact, it was site C in this case, towards or to the VPN to site A. So it's okay, but the other site respond, but nothing else happens. No ESP packet, no more child essay or say negotiation or whatever, nothing more. If we are curious, we can go to the response, and in this response, we only see the message, no proposal chosen. It means that the site A is not satisfied by the proposal of the site C. But the site A also tried to do something towards the site C, but without a response. And you see that the first hints for troubleshooting is that the exchange type are not the same. In one case, it's IKS Init. In the other case, when coming from the site A, it's identity protection. And also the main point, it speaks or it talks of main mode. Main mode is a characteristic term for the version 1. In the version 1, you can have main mode or aggressive mode. So it means probably that the site A wants to use version 1 and the site B or site C, to be correct, intends to use the version 2. We can confirm this, and this is the case there. We have a column with the version, and we see, it's obvious now, we see version 2 for the 2 exchange and version 1 for the other one. It means that the site A is able to answer to with a version 2 answer, but when it when the site wants to trigger the VPN, it prefers the version 1 by default. So that it is a configuration where it is incompatible setup of the tunnel, because version 1 and version 2, as said before, are totally incompatible. But our same site could use version 1 and version 2, but not inside the same tunnel or same VPN. In this case also, we don't have to see the unencrypted packets. The ciphered version is sufficient. Yes, I still some time. Yeah. First, case, third case. In this case, no child, but if we open troubleshoot B, if we stay stuck with the encrypted packets, it's not very useful. We see that there is a beginning of the negotiation. We see the Iksa, we see the auth packets. We have some informational exchange, and we have also a create child exchange, but nothing further. So apparently something is wrong, but since in this response everything is encrypted, nothing useful could be extracted from these packets. So we need the deciphered packets, and yep. In this case, I'm not totally sure that apparently there's something wrong with my but it's still in the slide. In this case, we see that the answer is TS unacceptable. And TS unacceptable means that there are some discrepancy between the traffic selectors of the two sites. So it's a difficult case since we are not able to have these unencrypted packets usually. So in this case, the main source of information will be probably the logs of the two devices, more than the use of Wireshark. With Wireshark, we can only see at which step the problem occurs, but not what is the problem, what the problem is. And let's see this one to finish. I think I'm yeah, at the end of my presentation. In this case, we have just create child exchange. But there, same thing, ciphered, so no visibility. If I'm able to gather the keys and to enter them in the Wireshark, I could decipher and then say the message, no proposal chosen. In this case, it means that something is wrong in the settings of the parameters. It could be the authentication, could be the Deciphering algorithm, or whatever. It could be the defilement group, this kind of thing. So I've put a couple of minutes. Yeah, just one other example with, in this case, for example, a mobile V2 case, and I think I will end my presentation by this. In this case, we can see it was a tablet connecting to a firewall, so I can see the SA init exchange, and after that I can see the there were more exchanges. I don't know exactly why, because I didn't study this case in detail, but after that we see that it's successful, since we have some exchanges in ESP. And in this case, since the remote device is behind a box somewhere in France, some NAT is involved, at least one or perhaps twice, since it's a 4G device. It's a 4G router, to be more precise. So we see that we switch from 400 ports to the 4500 ports, both for the IKE exchange and also for the ESP exchange. But something I want to point is that we can see that in this case, we are not using the usual port to answer to the first exchange, to the first message. In this case, you see that we are using the 1525 port to answer. Because as we are using several translating devices, we can see that the first exchange was made with the source port 1525 and not the usual 500 port. It means that the 500 port is not a compulsory port. Since we have to deal with the NAT translation, we have to deal with ports, source ports, that could be different from the usual IPsec or IKE ports. And it's written in the RFC that the firewall or the device must respond whatever source ports it sees in the coming into the coming packets. So I think I will finish my presentation there. There are some time for some question if I see that in the discussion or in the question and answers panel, so there are some exchanges. Just before before answering, at least I hope I will be able to answer some of the questions. Don't forget to complete the survey. It's useful for the SharkFest team. It's also useful for me to know if the presentation was useful, if there is some improvement to do for the potential next sessions. Regarding the questions in the question and answers panel, how many packets need to be lost for renegotiating a security association? It depends on the security association. In fact, there are two kinds of security association. One for what we called in the version 1, phase 1, or the parent SA, and one for the child SA. For these security associations, there could be, at least for the child SA, there are mainly two two things that could trigger renegotiation. An ordinary renegotiation, that is to say, on our working VPN. The first one is the time. When you build an essay, you define the length or the duration of this essay. You can have 1 hour, 2 hours, 8 hours, or whatever. And after the expiration of this duration, your side has to renegotiate the SA. In version 2, you can have a different time in each site. So it would be 1 hour for site A, 8 hours for site B. And the first timer to 0 triggers a new negotiation. It's the first case, the most current, I would say. Another possibility is also to take into account the amount of data that were exchanged. Since the hackers can benefit from a huge amount of data, most of them are a long or a lengthy exchange. They can find useful things on a perhaps 1 hour duration if there are a huge amount of data exchange. So you can say, after exchanging perhaps 100 megabytes or whatever, I need to renegotiate to refresh the keys used, especially in the data, in the user data steps. Since in user data steps, the user data that you exchange will perhaps be still useful in 1 year, 2 years, and if the keys are not refreshed quickly enough, it could be an opportunity. I'm not an expert in cryptography, but there could be an opportunity to recover the keys or to be able to decipher the user data, perhaps in 1 year, 2 years, or whatever. And so it's important also to limit the attack surface that we offer to the hacker. So timer and or amount of data could be an event triggering the negotiation. There could be also another case is one side restarts or whatever, and in this case there could be a dead peer detection, and according to the settings of each site, this could lead, if we detect that our peer is out of order, or at least has been out of order, we can try to rebuild the VPN. So it's another case of negotiation. So to answer the last question, SA timer need to match both sides? No, not anymore, I would say. It was the case in version 1 and in some implementation of this version 1. Now it's totally independent. The site A and site B could define different timers. It's not a problem. It's only the first timer or the first data quota that is reached that leads to a rebuild of the SA. The FQDN in the capture, yeah. I have to remember in what file I found this. Yeah. In this, for example, in this profile, I've added a column for ID FQDN. In fact, this ID FQDN will be found in the IK auth packets, and more precisely, in decrypted data, contain data, in the payload named identification. Identification for the initiator. Yep, there I am. And same thing for the responder. Okay. Is there any other question?
I think there might have been one. I'm not sure if you answered. So our key is not available with LibreSwan/OpenSwan.
I'm not totally sure that I've understood the questions. Yeah. I don't know, to be honest. I've not tested all the implementation of IPsec version, so I don't know if we can recover the keys in other packages than StrongSwan. I don't know if other attendees can help me in this for this question. If there is something possible with OpenSwan or LibreSwan, but honestly, I don't know. I have not tested this this package, at least not for this function. And is there any other question? Yeah, I think I'm almost done. Yeah. So no more questions?
I think there are no more questions, looks like.
Okay, so thank you everyone for attending this presentation.